So, another way to study systems is to perform free energy calculations. Firstly, why do we do those free energy calculations? Let's say that we want to investigate some phenomena and we're thinking to compare it with our computational technique, right? So the phenomena which you might see in your experiments might take hours, might take minutes, and so on. But classical molecular dynamics simulations cannot take this kind of time range. It maybe will go to microseconds, or if it's coarse grained, maybe to milliseconds. So you will never reach that time scale when the phenomena is happening. And then if you have starting configuration which will take a longer time to equilibrate and to reach that state which you want to observe, basically what will happen that you might never observe that state of the system. You will not see this phenomena. So free energy calculations are basically done in order to push the systems to reach that kind of state. And so out of free energy value you can see that if the Gibbs free energy is positive, then the certain process can go or reaction can go spontaneously at the studied condition. If the Gibbs free energy is negative, then the process can go spontaneously. So basically what we're gonna see in the simulations then, so maybe we'll see this phenomenon, but still it will not be sure unless you do free energy calculations. So in some cases, like for instance molecule penetrating from membranes, or if you want to see binding of something to something, it's a very good idea to perform this kind of calculations. So there are many kinds of free energy calculations. I will tell you today about these 4 calculations, because the last one is maybe not so much used for comparing the scattering techniques with what you see with simulations. So the first is umbrella sampling. Umbrella sampling is kind of a method which is using artificial harmonic restraint when you try to along the reaction coordinate. So which can be like binding of something to something, so it depends on what you call as a reaction or maybe phenomena. So basically you create several kind of simulations, which like windows, several simulation boxes over the reaction coordinates, and then you simulate in every window your phenomena. Let's say you run simulations. In the end, all the simulations, they build this kind of free energy landscape, or so-called potential of mean force. So you in the end perform a weighted histogram analysis to combine all the sample data in different windows in the most optimal way. Another methodology is replica exchange molecular dynamics. So this method also is using very many calculations in order to scan the free energy landscape, and moreover those calculations should be done at different temperatures. So coordinates are exchanged between independent simulations or replicas at different temperatures based on Monte Carlo criterion, and the exchange probability is listed here. So that the temperature must become sufficiently high to ensure that no replicas become trapped in a local energy minima. Yeah, as the previous method, this method has this advantage that you have to create so many simulations, and it's very time consuming. Another methodology is metadynamics, and that method includes different kinds of metadynamic simulations like well-tempered metadynamics, smooth-tempered metadynamics, and so on. So basically, in metadynamics you select collective variables, which can be distances between things, can be angles, can be dihedrals, and so on, and then you try to simulate over at reaction coordinate. And basically you are applying some Gaussian potential, which will put your system in a certain state at each time step. And then you also decide after how many time steps you will add the new Gaussian functions in order to simulate your phenomena. It's a very useful method. You can run the continuously one simulations, or you can run several simulations parallel as you did it with the umbrella sampling, but you don't need to. In this case, you can do one simulation which might scan all the free energy landscape. Also, one of the advantages of this method is that metadynamics normally scans only the most interesting area of free energy landscapes without going to the ones which are not interesting. applications. So how do we think when we simulate systems? So if we have very large system, like some biological system, we still cannot go to simulate cells, so we have to take parts of it. Yeah. So if we have, let's say, membrane, a cell membrane with proteins and lipids, we might choose only lipid bilayer. Sometimes we can use something like let's say like lipid bilayer, maybe with a protein or maybe with peptide. So you always have to go down in sizes in order to simulate your systems. So here, for example, you see various allotropic phases can be simulated membranes in biomolecular applications. Also, you can simulate like microtubules, large objects, you can simulate nanoparticles and so on. And you can also simulate different kinds of materials like nanotubes or some kind of inorganic nanoparticles. You can simulate adsorptions on zeolites or adsorption on some surfaces. So which properties can be computed from simulations? So basically one can calculate sounds and SAX profiles and try to match them with the ones which come from experiment. However, as one disadvantage I can tell you that this process of calculation is very memory consuming, and you will not be able to go towards larger systems. It's maybe very good to develop your own code, because some codes are pretty much odd and they will not be able to handle very large trajectories. However, if you don't have so many different atomic types, you still might be able to calculate those profiles. Also, since we have the trajectory and molecular dynamic simulation, and we know that the trajectory looks the same each time we simulate. It starts from the same atoms and it's finished with the same atoms. At every frame it's basically the same order. We can always select the same atoms or the same group of atoms if we want to see their position over time. So here, for example, we see cholesterol in a lipid membrane. So here is the bilayer center if we look at. So we can, by selecting certain atoms, we can know their statistically most probable orientations. Like here we see OH groups and methyl groups. Or we can see the total distribution of the molecules. So which is very useful, and it can interpret what you see in scattering data, where you can see basically average profiles. So here you can see also electron density profiles examples, which can also be calculated from molecular dynamic simulations and compared with experimental data. Then dynamic scattering data can be computed. So for instance, self-intermediate scattering functions or even relaxation times can be calculated. So here you can see the comparison with the NMR, QENS and MD. And here you see, for example, since in the previous example I showed you that you can use for certain molecules, here you also can select, for example, the whole molecule and see how the relaxation of a certain molecule can affect the total relaxation of the whole system. If you have lipid membrane system, you can always calculate the area per lipid. However, this method is very good only when you have the same lipid head groups or something similar, because if you have different sizes, it still is very odd method, since you just take the box in XY direction and divide it by the number of lipids in a leaflet. Another way is less odd but more complicated, I would say, is to use some kind of Voronoi diagram with the Dione triangulations. It can give you quite accurate maybe areas per different kinds of molecules which you want to investigate. As you can see, they showed here in different colors. So yeah, as I was saying about free energy calculations, here is an example how you can study binding free energies of molecules at different surfaces, and like titanium dioxide. And here, for example, you can see how you can investigate the binding free energy of a particular molecule to a lipid bilayer. So this is also free energy calculations example of like reorientational or rotational free energies, which can help to understand if the rotation or reorientation is possible around certain angle or dihedral. Yeah. Other properties like radial distribution functions, you can calculate like different kinds of radial distribution functions. This is like 3D, and this is like in 2D in a certain plane, so you can study the clusters of molecules. Spatial distribution functions is a very nice feature which can be considered like as three-dimensional radial distribution functions. It can show you different kinds of shells like Salvation shells and so on, or water shell around the molecules. let's say if you don't have only scattering data, but you use, for example, NMR, you can also calculate the deuterium order parameters, which can tell you a lot of things about order, and particularly in molecular dynamic simulations, they are can be very accurately reproduced. I didn't show here error bars, but they are all within error bars. Then rotational and reorientational correlation functions can help to interpret the dynamic scattering data, which molecules or which part of the molecules rotating, let's say, or relaxing faster in this sense. Then hydrogen bonds. So we all know that some system or like a lot of materials are depending on the hydrogen bonds, and here, for example, one can study hydrogen bonds over the time and understand what happens in a, for example, protein system during the time. So another thing is the residence time. You can select certain molecules and see the residence time on the surfaces of other, let's say, nanoparticles or inorganic surfaces. And that kind of residence time can explain you which surface is better for binding molecules. Then since you can get the structural information from molecular dynamic simulation, basically coordinates, you can calculate secondary structures of proteins and peptides over time, get the most statistical probable secondary structures, and there you have these secondary structures decoded as colors. And here peptides shown like different colors, different amino acids, amino acid residues. So also you can calculate the contact maps. So here, for example, you see the contact maps between myoglobin. So on diagonal you see within the same proteins, and on the triangles you see the points between different proteins. And out of the number of points, for example, here you can see that how well clustering is happening between different proteins. They can help to explain if you see, for example, protein aggregation process in your systems. So another property is the diffusion coefficient. So they are not so much accurate as you can see in experiments. So for the same temperatures you can have different kind of values, but also similar uncertainty can be done for MD. But still I can say that there are comparable order. When it's comparable order, one can certainly draw conclusions about what happens in your systems, or if your models were well developed so that they can reproduce closely the experimental data. Root mean square deviation, also it's another measure of structural distance between coordinates. And so basically this helps us to determine if it's time for us to do some production run or to investigate system properties. So it's very desired to investigate such properties when the system is in equilibrium state. So basically when we see that it converges to or fluctuates around the same line, we can certainly do that. So summary, so before selecting any kind of methods you have to consider a system size and think of what properties you want to compare. Moreover, if you want to do it by yourself, you have to think about your resources, CPU, GPU resources, and memory resources, and storage. Because if you want to have output from your simulations more often, you will need very good storage. And also to consider the process which you want to investigate, not only out of your experimental opportunities, like which experimental technique you use, but also on what scale such process can happen. And then you're gonna select the computational method. Also, it can be worth to use several computational techniques to compare or to interpret what you see in your experiments. So yeah, thank you very much for listening to this presentation.